Thank you very much. Thank you very much, Clark, for hosting us here. It's fantastic. I'm very, very happy to be here. Mike and Chandra are running here a workshop on formal verification, specifically on using our tool. I wanted to say a few words before they start. It's about Certora, about what we are building. So basically, these are the people who are actually not here. Shelly, who started Certora with me, John, who's actually going to be here later this week, and Nurit, who just left. We are actually trying to get this field of formal verification. It's actually a field which has been along for quite a while. We are trying to make it into a product, and we are interested to use people here to use this product. We have a lot of experience in this domain, based both theoretically and practically, but still we are still learning this space, and particularly we are learning the space of the DeFi. But our technology, in some sense, it's generic, and it's actually not specific in some sense. We will, of course, talk a lot about smart contract, but it's actually about checking correctness of code. And it's a big problem, but we think that in the domain of DeFi, it's actually more interesting. But the technology that we are developing is actually unique, independent. And one of the most thing which is frustrating for people working in code security, and there are actually studies by Google and others, that most of the interesting bugs that you have in software, they are not actually generic, they are more specific. They are related to the logic that the code is implemented. And you will see that the way we approach security in Certora, it's exactly tailored to that. So it's not actually a generic tool. Like there are people trying to check type checking, checking memory safety. It's not what we are doing. We are trying to do something which is specific to the code. And maybe another thing which is related to that is we are in the ecosystem. So there are a lot of people which have security, like auditors, and they're doing fantastic job, and some of them are better than others. Our tool is just trying to help them. We are not trying to replace them. We are actually working together with the auditors. And what do we do? And you will see it later in specifically Chandra will go into details. We have a tool. I like to think about it as somehow comparing two programs in some sense. So you compare, in one side you have the program. I don't know how to use this thing, but okay, you have the program here, the code. It could be in Solidity. Actually, our tool works on the EVM. It doesn't matter. And then you write the specification. We have our own language called CVL. And there you write, and it's meant to look like Solidity, but it's actually rather different from Solidity, and Mike will explain. But the idea is that it compares these two things. And it can either tell you that this program is correct, in a sense that it satisfies the property, but the most interesting case is that it gives you a violation. That's the most cases, that it gives you a violation. And actually, the most interesting, and you will see that it gives you a violation. Now, since we are talking about a problem which is computationally hard, and Clark will talk to you about it tomorrow, these tools is doomed to fail in certain cases. And basically, in the case that it fails, actually it times out. What does it mean? The solver, if something is under lease, is unable to give us a concise answer. So what we do here, we have to do something. We have to make the program more modular. We have to simplify the program. We have to do some things, and Mike will explain. So when there are failures, you have to do something. You have to help the tool. Please ask me questions. You can during this thing, I hope. If you and the beauty of this thing, and we have actually customers who are using it, like Maker Team, you heard if you were in DSS, and Trust Token, others. It's integrated into a normal development pipeline. So as part of your code, every time you are changing your code, you run this thing. So it's integrated into your CI if you work with Git, with Circle. And every time you change your code, assuming that you leave the specification the same, you check it. And of course, you can occasionally change the specification as well. Okay, so the idea is this tool is actually integrated with your dev team, and it makes your code more secure. And you can run it before the audit, after the audit, and we are finding bugs before the audit, after the audit, and it's fine. And the idea is, the more you run it, it makes sure that your code is secure with respect to the specification. The most thing that you can get from these 2 days, and actually that's one of the most interesting aspects of formal verification, is actually formal specification. And this goes back, of course, to the Greeks. Writing formal requirements about software. And you will hear from Mike a lot about it, and you will actually have exercises. So these are some kind of properties that you expect to hold in your program. So basically say that the color of the C is blue. So it means it must be blue, and if it's not blue, something is wrong. And the idea is invariant is something that you really, if the invariant is broken, then all things are lost. And our tool, you give it the invariant, and then it gives you violation. It automatically finds violation of this invariant. And of course, here in computer science, the person that actually advocates invariant the most is Dijkstra. All of you know Dijkstra, right? So Dijkstra invented, or basically at least he advocates using invariant. And he said that, look, before you start writing your program, you have to think of invariant. That's not necessarily the case. It's very, very hard to think of invariant. And also it's very hard for us to think of invariant. But gradually, we think of more and more invariant. So what does Certora does? Certora build tool, and you will hear today a bit about our tools. We have the CVL. This is a language that Mike will explain. It's a language for writing invariant and writing actually more interesting properties. It can compare programs. It can do relational properties. You can do many, many things. You can have modularity. This is the language, and we keep developing it. And then there is the Certora prover. This is the one that you have access to the key. And Chandra actually is working on mutation testing. This is a tool. I don't know if you will be able to explain it to you, Will, or? Briefly. So this is a tool that checks the specification. Because we have cases that people use Certora. How many of you are familiar with the Notional incident? 0. Okay, so Notional is a very interesting company, actually not very far from here. The guy who started this in Berkeley. Fantastic team. They work with the Certora team. They also work with fantastic auditors. And the guy wrote invariant. And of course, the auditor also checked the code, and the Certora tool also checked the code, and the Certora tool said that the invariant holds. And then Immunify. How many of you are aware of Immunify? Great. So somebody in Immunify found a bug in the code, and critical bug. It's a bug that allows you to do double spend. That's the worst thing you want to have in a smart contract, that you can use this to do double spend. And it's interesting, the owner of the protocol, when he received it, he said, look, this is what I wanted to prove with Certora. What's going on? And he's sending us messages. This is pretty scary, I must say. And we, of course, look, where's the problem, where's the bug in our tool, in the SMT? But of course, the bug was, in most of the cases, it was in the invariant. The invariant was tautology. What does it mean? It means that the invariant is the case it's not actually dependent on the program. If you say that 7 is greater than 5, the tool will be able to prove it. But it doesn't mean that your code is correct. It means that 7 is still greater than 5. So the invariant was kind of tricky, and that's why we have mutation testing. So now we can actually prevent it. So the idea is it wasn't a bug. It was a bug. It's something that in the specification had an error. And it's also interesting because it shows you something about this area of formal verification versus manual auditing. Nobody accused the manual auditor, and it's right because it's a human. And people accuse formal verification. It's a good idea because you have to accuse machines. You see it with automatic driving cars, whatever. If you make an accident in your car, it's okay. But if a self-driving automatic car is making a small accident, it's bad. So we are actually, and we have to be very careful. And some level of paranoia is very, very good when you're working, especially with formal verification. When the tool found a bug, it's great. When the tool verifies your property, be careful. Because maybe it's not even a problem in your tool, it's a problem in your property. Okay? Okay. So why are we doing it now? So there are a lot of reasons, and actually formal verification is a very, very rich field in computer science. A lot of very, very good work. It's go back actually Turing. The Turing in his first paper actually talked about formal verification. And then there are the people like I want to say the giant of this field. I already mentioned Dijkstra, but Hoare is a living legend, and he's actually developed some of the things. Actually, if you look into the CVL, is essentially whole logic. So it's actually a lot of things that developed very, very early in the 70s. Milner's work, Patrick Cousseau's abstract interpretation, Bob Floyd from here, actually from Stanford, he's a guy. So all of these were developed a very interesting technique. But then what happened, it actually happens in many fields in science, that people realize, and there's this very nice paper. How many of you familiar with this paper, the Milo, Lipton, Pellis? Yeah. Okay, so this paper, if you read it, after you read it, you don't want to do formal verification. Okay, it's like, it basically gives you a lot of fantastic reasons why not use formal verification. And it's actually a very good read. Actually, it's a very good read, and it makes some point that even me, working on this field, it's actually something interesting. And they make it actually one by one, actually explain you why you should not use formal verification. Okay? And it had dramatic aspect, at least from what I understand. I'm kind of, you see, I'm a bit old, but I came a bit after that. But it did, for example, at least in the US, it affects funding in this space. It's basically, I remember people say that if you want to get funding, say that you're not doing formal verification. Okay? But after that, it's interesting. Many people, including Clark here, works very hard. And now if you want to get funding, you say you work in formal verification. So people change the thing, and it's actually very interesting. A lot of good work. I want to point it out, the SMT solvers, you will hear tomorrow, static analysis, people have developed, and actually Certora is consuming all of it and doing it and doing more. So there are a lot of, and there's still, it's not actually the end game. I don't know what Clark thinks, but I think there's a lot to do. But actually the most, and here I pointed out Bill Gates' quote about formal verification. It's the SLAM, which actually use an algorithm which I developed for interprocedural. So this is actually, this thinker, so this is in order to prevent blue screen. It's in order to find correctness of device driver. So a lot of things came in this space, but I want to point out, maybe I'm using here Vitalik, but maybe it's Gazebo, that for the domain of smart contracts, it's actually the perfect domain for formal verification because code is low. And because you have this immutable code. And the idea is it's almost like hardware. It's the case that so smart contract or DeFi is almost like the perfect matching for formal verification. Because it's a case that really, if you have, usually formal verification is expensive. It's expensive in terms of human, it's expensive in terms of machines. And you will see this today and tomorrow. But the idea in this domain where you have billions of dollars, you want to do everything, including auditing, including formal verification, because you have so much money at stake. Okay? So how is Certora doing? So Certora is actually working with top protocols. And you can see here a lot of actually code was being secured by Certora. I think if you were in DSS, you had it, or you see also in the Maker website, in our website. We are running a lot of, the tool is running on a lot of code, and it's checking many, many lines of Solidity code. I think the most important data is here, is the number of hacks that we prevented. So basically, how many bugs are prevented by this tool? And I think this is the best way to value this technology. How many bugs have we prevented? And what I call prevented bug, I mean that it's a bug that was prevented before the code was deployed. Okay? We also have bugs that we have found because we are working on the EVM, but this is we have fewer of this. So we can work, of course, check code after it's deployed. But then it's much more complicated to fix than others. But this is the value of this technology, and I think it's the same for model checking technique. How many bugs have you prevented? So I want to again give you motivation. You will hear from Mike more technical, but I want to talk about the property that is more interesting, at least most interesting for DeFi, is solvency. And solvency intuitively means that if everybody runs to the bank, then you should still get your money. You should not lose your money. And we heard the sale issues, we heard this thing. And these are the kind of things that you will see today and tomorrow that you can formulate with our tool. And then I show you, here is just data of bugs that were found by a Certora prover. And the interesting thing, these are protocols which have enough money to use the best auditing team. And the tool went after them. Okay, it's of course useful to run before them. So these are bugs which were used after the thing. And you'll see that how much money is saved by this kind of technology. So these are the things that you run. So for example, in the Trident, this is a sushi thing. I don't know, you will show it or in some, no. But in the Trident, basically the tool found a bug that allows you to swap one token, $1 for the whole money. Okay, you give $1 and you get all the money. And it was found by the SMT solver actually. Okay, so you can get wild idea what to do here. So that's how is this prover compared to other technique? And I will talk later about interactive tools and other, but I'm talking about other tools. So there's manual audit. I said it's actually incomparable. You can find bugs after, people can find bugs after Certora, especially if you didn't have the right spec. You will find a bug in the manual audit. And Certora finds bug after manual audit because we write different specs. Of course, bug bounty is the same. I mentioned the notional case and others. We are more covering than fuzzing and testing because testing just gives you one behavior. Of course, testing and fuzzing is cheaper. So you can do that earlier and then run this. And there's tools like Certora that do static analysis. This is over approximation. It's incomparable. It's actually sometimes it gives you bugs which are not real. And actually in the example that you show, if you run our tool, you run the Certora, you will see that it gives you many, many errors, but the vast majority of them are not real. And our tool is different in the sense that you give this spec, and under certain conditions, the bugs that it gives you are real, in the sense that they violate at least your spec. It's not necessarily a bug, but at least it violates your spec. This is one example. If you were in the DSS, you have seen it, but it's kind of cute. I don't know what you think about it. It's an experience. It's an experiment. Basically, what the company did, this is TrueFi, and what they did is basically they injected bug manually, and they want to check who finds them. Okay? And again, I don't think I buy that because it's actually a very, very small experiment. But at least what you can see here is that 12 unique bugs were identified by the prover, and actually these bugs are bugs which all the auditor missed. Okay? And you can see also that there is one bug that an auditor found that the Certora prover missed because they didn't have the right invariant. Actually, this is a more interesting case. So this is the DAI, the maker DAO. Of course, everybody knows it. They have about 12% of the market. And what they did, they run the tool on the core contract, and they use the core invariant. The core invariant is basically saying that the DAI has enough money to pay. And the tool automatically found a bug, and it was very, very surprising to them, actually. And actually, it's a bug that can happen after a long time. But for us, since we think about invariant, it's actually very normal. It's basically find what we call in, and maybe Mike will explain it later, it's a counter-example to induction. It's a state which starts it's a transition which starts with a state which satisfies the invariant and goes to a state which violates the invariant. And this was found, and actually the Certora, the maker team, which is a fantastic team, actually, guided from Stanford, they wrote the tool, they wrote the rule on their own, and they found the bug. And it's great. It's actually something we love that. They're actually not using us. They're just using our technology. That's great. We like to have as many customers as possible like this. This is comparison. Actually, Everett is from this domain. I like to hear. So basically, this is somehow how we are doing in terms of academia. So I'm using here formal verification, but I'm using it in a bit loose sense. So I'm counting fuzzing and static analysis as formal verification. It doesn't matter. So these are tools, and I'm using here tools in the domain of smart contract, but they've been developing other tools outside smart contract. So Mitwheel is a tool by consensus. They do some kind of fuzzing, and Kidna is a tool by 12-bit fuzzing. Manticore is a tool by 12-bit that does fuzzing with some symbolic, and Certora is static analysis. All of these tools, they share in common that are easy to use in some sense. And they're also open source. You can try them. They're easy to use. The problem with them is that they really don't give you a lot of coverage. Most of the bugs that we have found, actually, it's very hard to replicate with this kind of technique. But they're good to use, at least as a beginning, because they are free and they are very easy to use. And then there's other extreme. This is something which has been developed a lot in the case of formal verification. These are all open source tools. People have used them to verify many, many interesting properties of system, like there is for example, in particular, this one, I don't have the name, but it's Coq. Coq was used to verify a real compiler. But the problem with this, and these are very powerful techniques, but it's very, very hard to use. Okay, so for example, the verification of the compiler took about 10 years. So I don't think you want to use them. And again, unless you have to have different ways to use them. And maybe I want to point out Daphne. Daphne is a fantastic research project, which is also open source, which is used by Amazon. They have actually the idea that you have actually a lot of things that you have in Certora. But what this required that every procedure has its specification, and it's not realistic. And it requires that you actually help the SMT. It's not what we want. So what do we want to do in Certora? And I don't know, you will judge in these 2 weeks if we are there or not. We basically want to have the benefit of that and that, okay? We are not there yet, but the idea is we want to make it not as easy to use as that, but close to that. And we want to make it almost as powerful. And in fact, we are getting closer to be, I don't know about Kay and Coq, but definitely it was related to Daphne. We are actually, in some cases, more powerful. And so we are trying to get as powerful as Daphne, and a bit, I don't want to say as easy as Meat-Hill, but somewhat as easy, as similar to Echidna. And in particular, if you look into Daphne, I didn't tell you, but if you want to work in Daphne, you have to work in your own programming language. That's not what we think we can do. Okay, we don't think we can teach people to program differently. That's not the stake that we have Certora. We want people to write in their own programming language. And in particular, they write in Solidity. We convert it to EVM. And later, we will do it in Solana. They write in Rust. We handle the executable code. And this gives us an additional benefit because we also check the compiler. So we run the executable code. We make the specification easy to use. And we'll, of course, do something similar to Daphne. We rely on modularity, but modularity is optional. When the tool fails, we can write specification, and it's, of course, at the end, it could be as hard as Daphne. But we want to actually get to that later, okay? I think I'm done. I want to just tell you a few things about formal verification, and again, it's a bit subjective. It's but some of it is actually agreed in the community. So my take from formal verification, I already alluded to that, is that formal verification is not just proving absence of bugs. The biggest value of formal verification is finding hard to find bugs. Bugs that is very hard to find without formal verification. And again, this is not my experience. People have tried to use formal verification hardware. They reach exactly the same result. So I think it's hardware, software is similar. The other thing, also go back to hardware, is that the problem is not just the SMT. The biggest problem, and this is why we are here, is actually writing the spec. And this is actually what we need, people like you. Another thing which is interesting about formal verification, it's also interesting from a research perspective, is that you can do many, many things in formal verification on tricky code by being ignorant. So the idea is that you actually want to forget a lot of things about your code. You actually do not need to understand it. So modularity is a key thing. If I call your procedure, I don't need to know exactly what this procedure is doing. And again, this goes back to Dijkstra and others and Hoare that observed that with abstraction. So the idea is you actually don't need to model everything. For example, in the Solidity, there is this idea of gas. And the idea of gas is somehow guaranteed termination. Okay, so basically you have a gas that you can actually say that if you run out of gas. But for most applications, when you are trying to prove safety, gas is not relevant. So you don't actually want to be related on gas. So that's the idea. You have to somehow use that in a good way. Another thing, and that's also people sometimes want to say, we are not trying to replace the auditing or testing or anything. We are trying to help the auditing. Okay, it's very important and to make the procedure better. And you've seen even what you see, the comparison of trust token. It doesn't mean that we want to remove the auditor. And maybe the most important thing, and that's what I think is where I hope you can get from here, is that formal verification is not a one-time deal, and it's not something that you do at the end. When we talk to customers, they always tell us, look, wait, we want to use formal verification in a few months, and then they come to us and they've been hacked, okay? We don't want it. We want them to use the formal verification as early as possible, because first of all, it's easy to do it when the code is simpler. And also, you want the formal verification to be progress when the code is progress. And that's why we are hoping to work with you earlier. And basically, every time you change the code, you want to guarantee the upgrade. Thank you. I think then you will have the real thing. Do you have questions or?
It's like an interactive alias, like instead of SaaS. Gartner made another concept that it's like alias, interactive analysis.
Interactive term proving?
Yeah.
So what I'm saying, our tool at the end is interactive. But what we are trying to do, we are trying to make as fewer interactions as possible. Okay, so the feeling of using the tool, and you will see it, at least the initial feeling of the tool is using unit test. Okay, it's not like exactly unit test, but you will see. But the idea is you run the tool.
The concept actually is interactive application security testing. The leader of the market, I think right now, it's Contrast.
So you have to teach me. Okay.
I cannot teach you anything.
No. So, so you are talking not in terms of formal verification.
I'm trying to put this service or this tooling into the range of other kind of verification that are more for the traditional computing instead of just security contracts auditing.
Yeah.
The market is huge, so the big guys like Veracode, for example, I don't know, just to compare and put you in the correct place where you.
Yeah. So I think you are absolutely right. I'm probably not the expert here, but I do know that at least in the European they have ISO standard. That's what you're talking about. So in these cases, I think people have tried. Like there was here a company by a Stanford student, Dawson, and they actually, and then they passed a law that they said that you have to have some tools. But I think the formal verification, for what I understand, is not yet a standard there. And the reason it is not standard because it's too expensive, and people cannot enforce this kind of thing. People are using formal verification in a minor thing. Like I've worked with avionics software, but then you also verify some very, very small part of the code. It's very hard to apply, and you will see this technology is not as easy to apply as the other tools that you have.
For critical pieces of software instead of everything.
Exactly. Exactly. So people are trying to push. I forgot there's a company called QNX in Canada. So they're trying to push, and they are trying to gradually push the use of formal verification for small things. There is in Australia, Cell4. So there are efforts. I think that it's interesting that the DeFi is in some sense leading here because but even though it's such a new domain. More questions? Okay, I'll let Mike start the real thing.